Hello everyone. I am Deeptika, a third year BTech ECE student from Amrita Vishwavidyapitham, Coimbatore. I would like to present my final internship project here at Emertxe, that is simulation of washing machine using PICSIMLab. Before jumping into the project, let's understand what embedded systems are. Unlike general computers, which are good at more generalized tasks, embedded systems are special purpose computing systems which are designed to perform a specific task. So, it combines both hardware and software, and it is typically a part of a bigger system. And these embedded systems work in real time, which means they must respond quickly and predictably to inputs. It has a variety of components such as a microcontroller or a microprocessor, which we look into further detail, a memory, input-output interfaces, and other peripherals as well. So here are a list of few examples which comes under embedded systems, such as digital cameras, microwave ovens, washing machines, photocopies, etc. Now moving on to the types of embedded systems. So the embedded systems can be grouped into four main types based on how complex they are and what role they play in a device. So first we have the standalone embedded systems. Now these don't depend on a host system to work. They take the input, process it, and give the output all by themselves. That is, things like calculators and microwave ovens fall into this category. Next up we have real-time embedded systems. Now, these are designed to respond to inputs within a guaranteed time frame. They are used in places where timing is critical, like medical devices or automotive control systems, in such cases. Then we have networked embedded systems, which are connected to a network to communicate with other devices. For example, devices in smart homes or industrial automation setups, they often exchange data with each other through networks. And finally, we have mobile embedded systems. Now, these are compact and battery powered ones, like the ones which are found in smartphones, smartwatches, or cameras. And they combine processing power with portability, which means you can carry them wherever you want. So that's how it comes mobile embedded systems. Moving on to the components of embedded systems. Firstly, we have the input devices. These input devices include sensors, buttons, switches, etc. The information that is been extracted from the environment, it is usually analog in nature, which means it is continuous. And our microprocessor or a microcontroller cannot process analog information. And we need a conversion. So that is exactly what ADC does. ADC is analog to digital converter, which converts the analog information into digital information, which our microcontroller can process. And the digital information is again converted back into analog information, and it is let out with the help of output devices, that is actuators. So these generally include buzzers, display devices, etc., like motors, etc. And apart from these main components, we also have memory. Now, this memory is used to store the program code and the data the system works with. And there are also communication interfaces which allow the system to talk to other systems or devices through protocols like UART, SPI, or I2C. Yes. Now, C language is widely used in embedded systems for a variety of reasons. Firstly, it is close to hardware. As an embedded systems engineer, it is really important to have a good command over memory because embedded devices usually lack resources, and hence efficient handling of memory, it is something which is really important. And C allows direct access to memory and hardware through pointers and registers. So in this way, it can easily manage direct memory. Secondly, C programs are compact and offer high performance, which are even suitable for resource-constrained embedded devices. And thirdly, the C code can be reused across different microcontrollers with very minimal changes. So it also has that efficient part of portability as well. And C supports libraries for mathematical functions and input-output operations and encourages modular design, making the code easier to debug and scale up to different levels. And since ages, C has remained one of the important or most dominant languages when it comes to industry standards due to its balance of control and abstraction. So C is widely used in embedded systems. Now let's briefly have a look at a few important concepts in C. First, data types. Data types determine the nature of the data a variable can store, such as an integer, float, or character. Now, they can also define the memory size and the range of values that can be used. There are generally four types, that is character data type, integer data type, float data type, and double. Character typically has 1 byte of memory allocated, which is used to store a single character or a small integer. An integer data type has 2 or 4 bytes of memory allocated depending on the compiler, and which is used to store integral values, that is both positive and negative values. Float has 4 bytes of memory allocated, used to store a single precision floating point. And double, which has 8 bytes of memory allocated, which is used to store a double precision floating point. That is, float and double can be used to store decimal point values as well, depending on their required precision. Next up, we have operators. Now, operators are special symbols that perform specific operations on variables and values known as operands. So, based on the type or the number of operands, we have unary operator, binary operator, and ternary operators. Unary operators typically work around single operand, and one such example is the increment and the decrement operator, which is used to increase or decrease a value by one factor. And in binary operators, we have arithmetic operators, which are used to perform basic mathematical operations, relational operators, which are used for comparisons, logical operators, which are used to combine or invert conditions, and bitwise operators, which are used for bit level manipulation, and finally assignment operators, which are used to assign or update values. And in addition to it, we also have a ternary operator, which is like a short form of if and else statements. Moving on to arrays in C. An array is a collection of elements of the same data type which are stored in contiguous memory locations, which means they are continuously stored one after the other. And it allows multiple values to be stored under a single variable name. For example, as you can see here, we have an array ARR with its size 5, which stores different values like 2, 4, 8, 12, and 16. And as you can see here, the memory allocated is starting from index 0. That is, the array elements are accessed using zero-based indexing. The first address is based on 0 indexing. So it starts from 0, 1, 2, 3, and so on. And C supports both one-dimensional and multi-dimensional arrays as well. Strings in C. A string is a sequence of characters. So it's really just a collection of characters stored next to each other in a memory. But what makes it a string is that it always ends with a special null character, that is \0. Now this tells the program where the string finishes. We usually declare strings as character arrays. Now you can either assign them using double quotes, which adds the null character automatically, or list each character manually and end it with a \0. That is a null character. And it is important to understand that without that null character, the array won't behave like a proper string, and the functions that work with the string might not know where to stop. And C also gives a set of functions in the string.h library to work with strings like copying, comparing, and finding their length, etc. Next up we have pointers. A pointer is a variable that stores the memory address of another variable, and the address of operator is used to get the address of a variable. So here in this example, as you can see, we have two variables. So one is the pointer variable, that is PTR, which stores the address of the variable VAR. So now when you try to access, that is when you try to print PTR, you get the value that is stored in PTR, which is basically the address of the variable VAR. So this value gets printed. And at the same time, you also have a dereference operator, which can access or modify the value which is present at the address a pointer refers to. So similarly, if you try printing star PTR, the pointer basically goes to that address pointed by it. It does not print this address, but accesses the value that is being stored in that address, which in our case is 10. So these are the two differences that is really important to understand. And pointers enable efficient memory access, dynamic memory allocation, and parameter passing by reference also. And sometimes improper usage of pointers can lead to undefined behavior in the program. Finally, we have functions in C. A function is a block of code that performs a specific task, and they can be called multiple times within a program. Now, these generally ensure code reusability. So here is a basic syntax of how a function is defined. First, we have the function definition. So it generally has three parts like declaration, function definition, and function call. So here we have the function definition. These are called the parameters, which can be passed by a value or by reference using pointers. And the function can either have or may not have a return value. Now these includes the main part of the program where you can call the function n number of times. So whenever the function is being called, it goes to that particular function, executes the set of codes, and then returns back to the main program. So in this way, it offers modularity and code reusability, making the program more organized and structured in its own way. And function prototypes are typically declared before the main function to inform the compiler about the function's existence. Well, now let's first understand the fundamentals, that is the difference between a microprocessor and a microcontroller. Now, a microprocessor is essentially the brain of the computing system. It performs all the arithmetic and logical operations, but it doesn't have built-in memory or peripherals. That means it needs external RAM, ROM, and other input-output components in order to function. And because of this, it's mostly used in high-performance applications like PCs, servers, and workstations. And some of the examples include Intel Core i5, AMD Ryzen, so all the processors that we have in our laptops. So these are microprocessors. Now, moving on, what is a microcontroller then? Now, a microcontroller is a self-contained unit. It has the CPU, memory, input-output ports, timers, and all other peripherals, which are all packed into one single chip. Now, this makes it perfect for real-time and application-specific tasks, especially when it comes to embedded systems. It's efficient, compact, and does not need any external support to function also. And some of the examples are displayed here. So it includes the PIC16F877A microcontroller. That is the one which we're using in our project. Atmega 328, 8051, and STM32 are all some of the examples of microcontrollers. And now moving on to the types of memory. Memory in embedded systems is generally grouped into three categories. Primary memory, which includes RAM, that is random access memory, which is temporary and volatile, and ROM, which is permanent and stores the firmware. Now, RAM is further divided into SRAM and DRAM. That is, SRAM, static RAM, is fast and used for registers, while DRAM, dynamic RAM, is slower and needs to refresh constantly. Now, ROM comes in different types. That is, PROM, that can be written only once, while EPROM can be erased with the UV light, and EEPROM can be electrically erased and reused multiple times. Secondly, we have the secondary memory, which is used for long-term storage, like hard drives or SD cards. Though it's less common in low-end embedded systems, it's still used. And then there's cache memory, which is high-speed memory that is closer to the CPU, used to store frequently accessed data and helps in reducing the access time. So this project is built around the PIC16F877A, an 8-bit microcontroller from Microchip Technology. It uses the Harvard architecture, which separates program and data memory, allowing faster execution. So here are some of its key features. 14 kilobytes of flash memory for program storage, 368 bytes of RAM, and 256 bytes of EEPROM. It features 33 input-output pins across 5 ports, a 10-bit ADC with 8 channels, 3 timers, and 2 CCP modules for pulse width modulation. And it also supports USART, SPI, and I2C communication. So all of this makes it a solid choice for small control-based applications like the one that we're doing today, washing machine simulator. Now let us quickly look at the peripherals that are being used for this project. So first we have CLCD, which is Character Liquid Crystal Display. It is an output device which is used to display the ASCII text and custom characters. And it exists in two common types, that is 16 cross 2 and 16 cross 4. So in 16 cross 2, it has 2 lines, whereas in 16 cross 4, we have 4 lines, with each line accommodating up to 16 characters. Now, this CLCD communicates with the microcontroller in two modes. So, first one is the 4-bit mode and the other is the 8-bit mode. So, in 4-bit mode, it saves pins by using only the higher 4 data lines, whereas in 8-bit mode, more number of input-output lines are used, but it transfers the data faster. Now, this CLCD helps make the system more interactive and user-friendly by showing real-time status updates. As you can see in the image here, it states press key 5 to power on washing machine, and the interactions between the user and the washing machine, which is trying to display the output messages, all will be reflected in CLCD. Next up, tactile switches. Tactile switches are small push buttons that are used to take user input. When pressed, they connect the microcontroller's input pin to ground, and when released, the pin is pulled high again. And port B pins are used for switch inputs. So in this project, 4 switches are used. That is, RB3 is used for navigation. Short press is used to scroll, while long press is used to select options. RB4 is used to power on or resume operation. RB5 is used to stop or pause the ongoing program, and RB0 is used for indicating door whether like it's open or closed. So now let's understand interrupts. An interrupt is a mechanism that temporarily pauses the normal execution of a program in order to respond to an urgent event. Now, they are generally classified into two types, hardware and software interrupts. So, interrupts created by a hardware peripheral or a component comes under hardware, and software interrupts, basically when a program creates an interrupt, it comes under software interrupts. Hardware is further divided into maskable and non-maskable interrupts. Maskable interrupts, we can mask it if it's not important, while non-maskable ones, it cannot be skipped because they are really urgent to handle. Now let's say the washing machine door is opened midway while the program or while the washing machine is running. So as you can see in this example, there is this program flow, and whenever that interrupt occurs, it goes to the interrupt handler. So there are two types of interrupt handlers. One is IVT and the other is ISR. IVT is interrupt vector table, which has a fixed memory location that stores the address of the code that has to be executed whenever an interrupt occurs. And ISR, it is the block of code that runs in response to an interrupt handling a specific task. So once the interrupt handler handles the interrupt, it like once the program execution is done, it returns back to the main flow of the program to continue the process. So this is basically pretty much it. A timer is one of the most important peripherals that we will be using in this project. So the timers are used to generate delays, measure time intervals, or even trigger interrupts. The PIC16F877A microcontroller has three timers. Timer 0, which is 8-bit, timer 1 with 16 bits, and timer 2, which has 8 bits with the pulse with modulation support as well. Now, timer 2 works with two registers, PMR2 and PR2, and it also includes prescaler and a postscaler settings for more control. It can also generate interrupts when a match occurs, allowing precise timed execution of tasks. The last two peripherals that we will be using in this project are buzzer and fan. The buzzer is used to indicate the completion of the washing cycle, and it also provides a brief audio alert once the process is completed. So this helps the user track the washing status without having to visit the washing machine every time, like in order to give that audio alert so that like it makes it even more easier. The fan has been replicated to show the working of a drum motor in a washing machine. Now this runs continuously during the selected mode and automatically pauses when the door is opened and again resumes when it's closed again. And this adds both realism and safety to the simulation as well. These are the tools which are used in this project. First one is PICSIMLab. It is a real-time simulation platform that emulates the embedded hardware, that is the PIC16F877A microcontroller. It provides all the virtual peripherals like switches, LCDs virtually so that there's no need for physical hardware. We can test them online itself. Secondly, that is MPLAB X IDE, which is used as the integrated development environment, and XC8 Compiler is used to compile the C programs, especially for the 8-bit PIC microcontrollers. Now, all these tools offer a complete software environment for the development, simulation, and testing of our washing machine project. Now, let us quickly go through how the code is being implemented. Now the main logic begins in new main.c. This file includes a function called initconfig, so which is responsible for initializing all the core components like the CLCD, digital keypad, and timer. And it also enables the global and peripheral interrupts and sets the data direction for buzzer and fan here. Now the variables like operational mode and reset flag are defined globally here to manage different states of the washing machine like mode selection and reset or pause, etc. And then we have main.h. So this includes all the necessary header files and defines constants like screen IDs, reset values, and all the pin configurations. So this basically helps the code cleaner and making it easier to manage, especially when you're working with multiple modes and hardware features. It's essential to have an efficient usage of header files. So header.h declares all the function prototypes for different screens and functionalities, like displaying the washing program, setting time, checking the door status, and so on. And these functions are implemented in function def.c. The file function def.c contains the main logic that controls the entire user interaction between the user and the washing machine. So we have declared two arrays, washing program and water level. Washing program contains the program type, that is whether it's daily, heavy, delicates, white, sustain, wash, etc. And water level contains the 5 different modes of water level that is indicated by the user. Then the power on screen is a simple startup animation that prints the blocks across all the CLCD lines with a small delay, followed by the welcome text, powering on, and a washing machine. So next we have the function washing program display. So it takes the input from a switch and allows the user to scroll through the different washing modes. If the user presses key 4, that is switch 4, the program number increments and wraps around once it reaches the last item. Next function is water level screen. So this lets the user cycle through the available water levels using a switch, and the screen updates in real time to show the selected level along with the next two options for the context. Then we have the run program function, which is the main function in the entire function def.c. It starts by checking if the door is open using the door status check, and if all the conditions are fine, it proceeds with the selected wash program. It displays the chosen program and the remaining time, and then calculates the wash, rinse, and spin durations based on the total time. And these variables are stored using wash time, rinse time, and spin time respectively. Now, depending on the current progress, the CLCD shows whether the machine is washing, rinsing, or in the spinning phase. If the user presses the pause button, the fan stops and the timer is disabled. And when the countdown reaches 0, the buzzer activates for 2 seconds and the message is displayed indicating that the program is completed. Now the door status check ensures that it basically indicates whether the door is open during the operation. The fan and the timer stop in that case, and a warning is displayed like door is open, please close the door. And the system waits until the door is closed before resuming. So together all these functions simulate a complete washing machine. And now let's have a look at our simulation. So this is the PICSIMLab and this is the PIC16F877A microcontroller. Now since I've already simulated it, let me reload the last hex file. So it shows press key 5 to power on the washing machine. Let me press key 5 and it shows loading, powering on washing machine. And the next screen moves on to the washing program. So in order to scroll between options, we can use RB3. So pressing it for shorter duration will help in scrolling, and pressing it, like giving it a longer press, will select that option. So we will scroll through daily, heavy, delicates, stain wash, eco cottons, woolens, bed sheets, rinse and dry, wash only, aqua, and again it keeps on looping itself. So let me press heavy, and once it's selected, it moves on to the next screen, which is water level. And again here we have 5 different modes: auto, low, medium, high, and max. So maybe let's go with high. The next screen shows that press switch SW5 to start and SW6 to stop. So to initiate the running of the washing machine, let's press switch 5. It shows that the program is heavy with time 57 seconds. So here we have used seconds to make sure that the program gets completed faster. So the same can be done with minutes as well. So once the program is started or initiated, the washing is initiated, the fan here starts running, which replicates the running of a motor in a washing machine. Now here the function corresponding is wash. So as and when the time decreases, it moves to rinse, and the timer here detects by 1 second every time. to simulate the counter in the washing machine. Now in between, if we need to pause, we can click SW6, that is switch 6 to pause, and again if we can click switch 5, it starts from where it was left. Now when the timer decreases and reaches a specific value, it moves from rinse to spin option. So in this time everything is working fine. Now program completed, and it is asking to remove the proofs. So this is indicated with a buzzer also. So this is how the entire washing machine program is simulated using PICSIMLab. Through this simulation, we have seen how core embedded system concepts like timers, interrupts, and peripheral control can come together to replicate the functionality of a real-life appliance, that is washing machine in our case. Working with the PIC16F877A microcontroller and using tools like MPLAB X IDE, XC8 Compiler, and PICSIMLab gave a solid understanding of both the hardware and software aspects of embedded development. And I would like to extend my sincere thanks to Emertxe Information Technologies for providing such a structured and application-oriented internship program. So this experience has definitely strengthened the foundation and confidence to build more complex and real-time embedded applications in future. Thank you.